So up till now we have seen how to generate the data. Now we will see that how to estimate the parameter of the already generated data. So if you have remembered now, we will start first with the linear model. So if you remember, we use the same code to generate the linear model, and then we have introduced the Gaussian noise, and the data was something like that after introducing the Gaussian noise. So if you want to estimate again the linear parameter, which are C and M, so you can use the method LM. LM gives you the parameter of the line which is associated with the data which we have right now. So X and Y is, for example, could be our given data. This could be the data which in line is having a linear model, but it is affected by a Gaussian noise. So how do we estimate that data? We will pass the value of y and x inside LM. Now this notation over here, this is called the formula notation. So this it means that y is a function of x. Okay, and if we have certain more dimension rather than one dimension, so we can add all those dimension by introducing a plus sign. So if we have, let's say, z dimension, so I can put so so we can write like that. So y will be interpreted now as a function of x and z. But right now we don't have that second variable z, so we will use this formula notation. So y is a function of x. Then we will run this, and we will get m as a model. So it basically gives us the linear model, which could be fitted over this data distribution. So let's see what value does m persist. So m has, so intercept is predicting as 176, which is, we have intercept as 23, but it's predicting 176. It's far beyond what the original value is. But x, the value over here is showing the basically the slope. So if you can see, it's 0.56, it's 0.52. So okay, slope doesn't differ that much, but yes, so we can see a huge variation in intercept. It's just because the standard deviation of our noise is so high that the data has nearly lost its linear behavior. So if you want to see the line, so this is the line that gives us the least square error, and this line will be fitted to this distribution. So if we are removing or we are lowering the standard deviation value, so let's 5. Generating the values again. Okay, and so you can see now the distribution is somewhat looking linear, and now we will estimate the parameters. And so the new estimated parameters are this x, you can see it's 0.56, but the intercept, it's giving the value which is far beyond what's actual intercept is, just because of this noise. So here you can see that if I'm using the values as it is, for example, I'm not adding any kind of noise. So uh, my y is now mx plus c, so I'm plotting the y. And then if I uh, parameterize this linear model, and let's see what's m value. So there you can see, okay, now it's giving us the exact value. But if we are introducing this sort of noise in the y, and then if we are measuring, so intercept does lose its accuracy, but the slope is somewhat near to the actual value. And also we can draw the line. Uh, so okay, this is the plot, and so this is the estimated line. All right. So now we are going to estimate one-dimensional Gaussian. So first of all, we'll generate the value, okay, and to generate random the random 100 Gaussian distribution, which has mean 50 and standard deviation 3. This is the command. Okay. Now in noise variable, we have that generated data. Now we are estimating the parameter value, which is we know that this should be around 50 and 3. We are using the function fit fit distribution, so it's written at FIT now this function is basically in a mass package. I've already told you, you don't have to install. It normally comes pre-installed, but you have to load it anyway to use it. So noise will be generated, but if I'm using this fit distribution, so okay, so it seems like I have already included the mass package, but okay. But if it shows sort of error, okay, I've already to show you the previous demo, I've already included this, but do not forget to include the mass package if you are running it for first time. So okay, so in MLE v1 I have my estimated parameter. So what does it contains? So let's see, mean is 49.81, which is fairly close to 50, and standard deviation is 3.0. So it's close to our standard deviation. So that's how using fit distribution you can measure the distribution according to using the basically it implements MLE, maximum likelihood estimation inside. So using that you can measure the or estimate the parameter, and yes, dense function is another parameter. So do not forget to enter the distribution that you are suspecting that, oh, okay, this data could be belong to this distribution. So do not forget to enter this value over here. So and obviously your data. So that's how you estimate 1D Gaussian. Now we will estimate 2D Gaussian. So the function which we will use over here is it could be used to estimate n-dimensional Gaussian, but for now, for an example, we will estimate 2D Gaussian only. So here, first of all, we will generate the data as we have generated previously. So in the behavior normal variable, we have our two-dimensional Gaussian data. Now you can see that this is we are using the MVN function. Now MVN function is the function which we have in MUL cluster or MVL cluster library. So okay, So you can see that this error could not find the function MVN. So now I think we have to install that library. I mean, you can anywhere install it. So let's install require. So load it. So it would be mclust library. Okay, mclust is loaded. Now we will use this MVN function. So what are the arguments of this MVN function? MVN is used to estimate a multi-dimensional Gaussian model, but still you have to specify which sort of Gaussian you want to measure. So if you are suspecting that your Gaussian is having dimensional covariance matrix in which anti-diagonal elements are zero, basically non-correlated, so you can give this xxi as an argument, or you can simply write diagonal as model name. If it is it's a spherical. Spherical means your diagonal element or the diagonal value of covariance matrix are same and anti-diagonal are zero. So correlated plus its projection to the bottom will be of circle. So that's why you can for estimating this kind of model you can write spherical or xii, whatever you want. And for this sort of distribution, ellipsoidal Gaussian, that means non-correlated, that means in your anti-diagonal also have certain value. So basically, sorry, not non-correlated, usually correlated attributes this Gaussian is having. If this is the as a parameter that you need to estimate. So in our case, we have already given this 5 and 5. So it would be okay if right now I'm here specifying the spherical Gaussian, but let me see that what happens if I specify the diagonal Gaussian. So I have applied MVN. Now if I'm seeing, I'm watching the value of M. So what I am getting here is, so this is the diagonal, the covariance matrix. So it's showing the value 4.86 and 4.9, which is closely near to 5. And then mean, okay, we have given mean as 2. So let's see what mean this model has estimated. So mean is 2.02 and 2.03. So okay, so mean is also nearly perfectly estimated. Okay, so if I'm using this instead of xxi, if I use xii, let's see what output it gives. Okay, so okay, so okay, now it's giving the output 4.91. So it's now much more near to what argument we have passed our covariance matrix. So as you can see, so do have a good if you have a good estimate regarding the covariance matrix, so you can tweak this model using this argument.